Hello students and welcome to Chemistry A. I'm Miss Slate and today we're going to talk a little bit about photons, energy, and the electromagnetic spectrum. First off, energy transferred by light comes in discrete amounts. So this is related to how we talked about the fact that while light does act like a wave, it also acts like a particle at the same time. So these discrete amounts of light are what we call photons. You can kind of think of them as like little packets of light waves. And based on their frequency of these photons, or the frequency of the waves, if you're thinking of light as a wave, that determines how much energy is transferred by the light. So energy is directly proportional to the frequency of light. Again, remembering that light acts like a wave and it acts like a particle at the same time. And we relate the energy and frequency of light through this equation, where E represents the energy of the light in joules. H is Planck's constant. He's the guy who worked all this stuff out. And his constant is 6.626 times 10 to the negative 34th joule seconds. And of course, lastly, that is the Greek letter nu, which is what we use for frequency. And our frequency is in units of hertz, or 1/seconds. This example says a photon of violet light has a frequency of 7.23 times 10 to the negative 14th hertz. What is the energy of the photon? Well, our equation for energy is equal to Planck's constant times frequency. So Planck's constant is 6.626 times 10 to the negative 34th joule seconds. And remember, folks, anything that's a constant, like Planck's constant, will always be given to you on a test, so you don't have to worry about memorizing constants. And then we're going to multiply that by the frequency, which was 7.23 times 10 to the negative 14th hertz. Remember, hertz is the same as 1/seconds, so when we multiply, hertz is going to cancel with the seconds. And we get, for our final answer, we get 4.79 times 10 to the negative 47th joules. Again, I rounded to just 3 significant figures because our original frequency has just 3 significant figures. Remember, constants, like Planck's constant, is considered to have infinite significant figures, so we never base our sig figs off the constant. Now let's talk about the electromagnetic spectrum. First off, electromagnetic EM waves are ripples in electric fields caused by moving charged particles. So if you've got an electric field, if you disturb the particles and cause them to move back and forth, that is what will produce an electromagnetic wave. And light is an example of an electromagnetic wave, even though it also acts like a particle simultaneously as acting like a wave. The electromagnetic spectrum is a range of electromagnetic waves and is typically divided into 7 regions. Although again, because it's a spectrum, each region kind of bleeds into the next. There's not a hard dividing line between them. These 7 regions are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. So here we can see an example of the electromagnetic spectrum. And at the very top, it is giving us the wavelengths of different types of waves. So the longest wavelength waves are radio waves on the far left. Gamma rays on the far right have the shortest wavelengths. And they also kind of give us some visuals to help us have an idea of how big those waves would be. So like radio waves, they have really long wavelengths. So their waves are like as long as a soccer field or a house. You get into something like a microwaves, they're a little bit smaller. They're going to be ranging more from like the size of a baseball to the size of like the dot that you see, right here. Then we start to get much smaller. Infrared light, those wavelengths are more like the size of your cells. Visible light, we're talking like the size of bacteria. Ultraviolet is like viruses. When we get all the way down to gamma rays are smaller than molecules, okay? So that kind of gives you an idea of the size of those different waves. They also give us some examples of sources of the different waves. So obviously radio is one source of radio waves, unsurprisingly. Microwave ovens can be a source of microwaves. Same can radar. Your cell phones and Wi-Fi also work off of microwaves. Infrared is usually released as like a form of heat. So like infrared cameras can like pick up on the heat emitted typically from living things. Visible light, obviously any light that we can detect with our eyes is visible light, which if you look at the whole electromagnetic spectrum, visible light is a very, very tiny part of it. So the light that our eyes are actually able to detect is just a very small amount of all the different electromagnetic waves that exist. And there are other creatures that can detect different types of electromagnetic waves. For example, some fish and some birds can actually detect ultraviolet light with their eyes. Certain types of snakes can detect infrared waves through pits on their face. And then the next line down there you can see is frequency. Again, the waves with the lowest frequency are radio waves. So radio waves have the longest wavelength, the lowest frequency, and they carry the least amount of energy. On the other hand, gamma rays on the far right have the shortest wavelengths and the highest frequencies, and they carry the most energy. And it's this amount of energy that they carry which is related to the difference between ionizing and non-ionizing radiation that we talked about in last chapter. Remember, visible light and everything to the left was non-ionizing? It's because it carries a relatively low amount of energy, right? Like visible light is carrying, like about a joule, between 1 and 10 joules of energy roughly. Or well, I guess not joules. The unit they're using on this one is electron volts. There are many different units of energy. While things like ultraviolet up to gamma rays, we know those are ionizing forms of radiation, they carry a lot more energy than the other types of electromagnetic waves. And that is the basics of light energy and the electromagnetic spectrum.